There we go. Okay, so today we start Unit 3, which is our unit on algebra. And to understand algebra, the first thing we have to talk about is a variable. And a variable can be used in a lot of different ways. No matter what way it is, a variable is a letter or a symbol that replaces a number. Now, within that definition of the variable, it can be used in a lot of different ways. It can be used as a placeholder. So it's just sitting there waiting for the value to be assigned to it. It can be used as an unknown with a definite value. What that would be is like in an equation where you have 3x plus 2 equals 20. It has a definite value, we just don't know what it is. And in that case, you can solve for it. And it can be used as a formula. Often the technical mathematical term for this is an expression. So you might have something like the number of studs required to build a wall is 12/16 times the length of the wall plus 1. That's if you're doing 16 inches on center. So those are formulas waiting for numbers to be put into them. Once you put in the length of the wall, that formula tells how many studs are required. And we're going to look at some of those applied formulas for construction once we get some of the basics down. So what we're going to focus on to start today is this placeholder. It is an unknown number that doesn't have a definite value yet. So I'm going to start out with a phrase like, let's make it a little bit trickier than that. 8 more than a number. So here we don't just have that variable, we have other numbers mixed in with it. How would we express this with symbols and numbers? 8 more than a number. What operation is it indicating here? Now, when you see more than or greater than, you often think of these symbols, the greater than or less than symbol, but that's not what we're talking about here. More than means we're adding 8. 8 more than a number means we're adding 8 to something. So it's indicating addition. And we could have, the number could be indicated by any letter or symbol that we choose to use. For today, we're just going to use the letter X. So X plus 8 is 8 more than a number. So now I always get this question, well, could it be 8 plus X? Well, in addition, doesn't matter what order we put those. Is X plus 8 the same thing as 8 plus X? Well, let's put a number in there for X. If I put in the number 3, is 3 plus 8 the same as 8 plus 3? No. Well, they both equal 11, right? So yes. Addition, and you don't need to remember this term, is something we call commutative. What that means is commutative means we can change the orders of the number. As long as the only operation we're doing is addition, we can change the order of the numbers and it's still the same. So X plus 8 and 8 plus X mean the same thing. So what I want you to do is we're going to take 2 minutes here. Actually, we're going to take 1 minute here. I'm going to have you partner with the person next to you, or maybe all 3 of you on the table if there's 3 of you there. And I want you to come up with at least 3 more phrases like this that mean either X plus 8 or 8 plus X. So just on your paper, talking to the person next to you quick, come up with 3 more phrases. So we've used 8 more than a number. Let's see what we come up with. What we came up with. I heard the obvious one come up out there. X plus 8, or a number plus 8. So good. That one's a good one. Anybody come up with anything different? Okay, y plus a number, y plus 8, whatever, y plus 6. Anybody come up with any others that don't have the word plus in them?
Yeah.
What'd you get?
X multiplied by 8.
Now careful, that would be multiplication, not addition. So. You might have a number increased by 8. That would be x plus 8 or 8 plus x. Here I had 8 more than a number. We'd use greater than a number. Here's the one that a lot of people forget about. The sum of a number and 8. And there are a lot of other phrases out there. If we took our time and dug through them, we can come up with them that mean addition. So now let's look at another one. Let's say I give you a number decreased by 3. What's that going to be in symbols? Somebody said it there. X or A or whatever minus 3. Perfect. The decreased by means we're subtracting 3. Now there's a lot of other ways to express this. So again, I'm going to give you about a minute to talk to the person next to you. See if you can come up with other ways, other phrases that would indicate X minus 3. Okay, so I heard, sorry. I heard X minus 3 or a number minus 3. What else did we have out there? I heard one. Somebody had a really good one that I overheard there.
7 taken away from n.
Okay. 7 taken away from n, or what? From a number. 7 taken away from a number or from n. Or whatever variable we want to use. Good. There were a couple other ones that I heard. One of them I overheard was similar to this one. The difference of a number and 3. Now, one I want to point out here, just because it can be a little confusing. Three less than a number. 3 less than a number is that number minus 3. If I say 3 is less than a number, that changes it slightly. Now we're going back to those symbols like that. 3 is less than a number is 3 is less than n or x or whatever letter we want to use there. So a very subtle difference there. Then we come up with others for a number minus 3 or x minus 3. Okay. So we can look at a number repeated 5 times. What operation is that one indicating? Multiplication, good. So a number repeated 5 times would be what in symbols? Could be that number x times 5, or more often when we're dealing with algebra, we just write it as 5x. So now there are a lot of other ways to express 5x or 5 times x. Again, I'll give you a minute or so to discuss with each other, see if you can come up with some other ways, other phrases that would indicate 5x or 5 times x. So what did we come up with? What'd you guys come up with? Anybody want to be brave? There we go. Perfect. 5 multiplied by x. Any others? There's the one that's so obvious you sometimes miss it. 5 times x. The product of 5 and a number or x, yep. Now, does it make a difference whether we say the product of 5 and a number or a number and 5? No, it doesn't. If it's x times 5 or 5 times x, it makes no difference. Because if I put a number in for x, let's say I put in the number 3. 3 times 5 and 5 times 3, they both equal what? 15. So, multiplication is also that commutative that we said for addition. So let's step back for just a second with our subtraction here. Is x minus 3 and 3 minus x the same thing? No, it's not. If we put a number in there for x, let's say we put in the number 5. 5 minus 3 and 3 minus 5 are two very different answers. One's a positive 2, one's a negative 2. So subtraction is not commutative. In algebra, we tend to design algebra around two operations, addition and multiplication. So where we started out last semester, we talked about the count and the name. And we said the two main, most basic math operations are addition and multiplication. Subtraction is a byproduct of addition, and multiplication is a byproduct, or division is a byproduct of multiplication. So these rules, commutative properties and other properties, only apply to addition and multiplication. So what if I give you the phrase, a number split 4 ways? What operation is that indicated? Division, good. The number split 4 ways is most likely x divided by 4, or we could write it in fraction form as x over 4. So again now, I want you to work with the person next to you, come up with a couple, try to come up with 3 other ways, or 3 other phrases that would indicate x divided by 4, or x over 4. So I'll give you a minute. Okay, I heard a couple of good ones there. Anybody want to share? There, I heard it. The quotient. You know, the quotient of a number and 4. Any others?
A number into 4.
Okay, let's look at that one. A number into 4. When you say a number into 4 or a number going into 4, technically that would be 4 divided by x, but you got the right idea. We'd be looking 4 into a number. Would be x divided by 4. Or 4 goes into a number. Same type of thing. I heard someone say the obvious one. A number or x divided by 4. Any others that you want to share? Okay, and there are, of course, others out there that if we dug far enough, we'd find several phrases that would indicate division for us. So the next step, a little bit more difficult, is to start putting them together. Excuse me. We're going to put together multiple operations. For example, I'm going to say 7 more than 3 times a number. What's that going to look like in symbols? Well, let's break it down piece by piece. 7 more than something indicates we're doing what? Adding 7. Good. 3 times a number? 3x. So 3x plus 7 is what that indicates. Wonder where that extra line came from. We might have 3 times the number increased by 7. What's that going to look like? Well, 3 times the number is what? Well, the same as what it was up here. 3x. What's increased by 7 mean? Adding 7. So it's just 2 different ways of saying the same thing. Three times the sum of a number and 7. What's this one going to be? This one's slightly different. It's not 3 times a number this time, it's 3 times the sum. The sum is the result of an addition problem or an addition action. So we're taking 3 times some result of an addition problem. What is it that we're adding? Perfect. A number. So what's that mean? X plus 7. Perfect. So that parentheses there, if we go back to our order of operations, is indicating that we have to do the addition first. And then the result of that addition, the sum, is multiplied by 3. The sum of 7 and 3 times a number. So this one, it says sum again, but does that mean we have to have parentheses? Well, it's the sum of 7 and what? Three times a number. So either 7 plus 3x or 3x plus 7, either way. Now, when we're dealing with variables like this, one of the other places we can use them is in an equation. And we're going to go over solving equations in a couple of classes. But for right now, we also need to be able to create equations. So we can add to these phrases saying seven more than 3 times the number, which is just what we had up above, is 25. So now this part here is exactly what we had in one of our examples up above. Excuse me. 7 more than 3 times the number is 3x plus 7, or 7 plus 3x. What does the is 25 mean? Well, is 25 means that that is equal to 25. So it's a full equation. And it said in a couple of classes we'll learn how to solve equations, so we'll actually be able, in that case, x actually has a value, and we can find out what that value is. We might have the difference of 3 times the number and 4 is equal to the sum of the number and 14. So now here, this becomes actually 2 problems. We have the is equal to in the middle here. That's an equal sign. What happens in front of that is a separate piece, a separate expression. The difference of 3 times the number and 4 is going to be what? Oops, I forgot to write 3 times a number. There we go. That might make more sense. So 3 times the number and 4, what's that going to look like? Well, 3 times the number is 3x. The difference of 3 times the number and 4 is minus 4. Difference means subtract. After the is equal to, we have the sum. What operation does that indicate? Sum indicates addition. Good. We're adding something. A number in 14 is x plus 14. We can look at geometric shapes and diagrams. Whoops, come on. So let's say I have a part that looks like this. And rather than having exact dimensions listed here, this part can be made different sizes. So it's not the actual dimension that's important, it's the ratio of the dimensions that's important. So this here might be x. This might be 2.5 times x. And this one here might be 2x. And if I want to now come up with an expression for the length of this, it's just a matter of adding those all together. X plus 2.5x plus 2x. Now coming up in a couple of classes, we'll look at how can we combine those. Since those are all x's, we should be able to combine them. And we can. The key is that x is really 1x. Just like if you have an inch, we don't usually say 1 inch, we just say an inch. Well, an x is really a 1x. Well, how about something a little bit more complicated than that? Let's look at this. I'm going to put numbers in this first example. So in this example here, if I'm assuming all those corners are square corners, what is the value of x? How do I find the value of x there? How much is x going to be here, guys? Careful. If you had the right idea, you got 24 minus 17 is going to give us There you go. So x is 7 inches. So now let's look at a similar picture. And we can use more than one variable. We might have 5y here and 3x, and I want to find the dimension z. How do I define that dimension z? Well, over here, we took 24 minus 17. We were able to find 7. Over here, it's going to be 5y minus 3x. The difference is we can't combine these because we don't know what numbers y and x are yet. That's going to be one of our next steps. So in this drawing, come up with an expression to describe that piece. We'll call it z. What is piece z equal to in terms of the other dimension? Oops, I already used z. Let's call it y, sorry. What is y equal to in terms of those other dimensions? Well, again, we can think of it like there's numbers there. So let's say this is 20 inches, 4 inches, and 10 inches. How would I find this dimension? Well, I'd start with 20, and then what would I do? I would subtract the 4 and the 10, right? Subtract 4, subtract 10. In fact, I could do it a couple of different ways. I could take the 20, subtract, okay, I could take the 20 and I could subtract 4 and I could subtract 10, or I could do 20 and I could subtract 4 plus 10 in parentheses. Very good. So over here, I can use either one of those strategies. I just have to include the variables. So I can start with 5z and either subtract 2x and then subtract 3.5x, or I could start with 5z and subtract, in parentheses, 2x plus 3.5x. Any questions? Okay, so we've got a break coming up in about 10 minutes here. What I'm going to do is I'm going to give you some work to work on for about 10 minutes before we take our break. Then we'll come back and I'll lecture a little bit more. I'll give my voice just a couple minutes to recover. In the big book, page 322 through 323, it's exercise 12-2. And page 364 through 366, exercise 14-3. So this one here is just expressions like x plus 7 or 3x minus 8 or whatever. This one here is actually, the second one is equations. So I'll have you guys work on those for about 9 or 10 minutes or so. We'll take our break and then we'll lecture a little bit more. Okay, so to start out the second half of the class, we're going to explore that second use of a variable. But to do that, we're going to do a little bit of review. About week 3 of last semester, we talked about something called order of operations. And we experienced it a little bit in the first 45 minutes of class here when we were dealing with, the sum of a number and whatever, or 4 times the sum, and how that worked out. And if you recall, we have 4 levels in our order of operations. The first level of priority was enclosing symbols. Those enclosing symbols could be parentheses. If you recall, we looked at fraction bars. Those will be coming up the most. Square roots or root symbols or enclosing symbol. There's several enclosing symbols. What's the second level of priority? Does anybody remember? That's step 3. Level 2 is exponents. There we go. Remember, exponents include powers and roots. We haven't really encountered those with our variables yet, but we will at some point. So then the third one, you said it before, is multiplication and division. Very good. And then the lowest level of priority is addition and perfect. So those are order of operations. So just some examples of problems that we run into. So for a problem like this, what do we have to do first? So we start out at the highest level of priority. Do we have any enclosing symbols here? Yes. We have a parenthesis. Stick with me, guys. So we're going to start out there inside that purple box, inside the parentheses. Now inside the parentheses, are there any other enclosing symbols? No other enclosing symbols, so we move down to level 2. Exponents. And we have 3 to the power of 2, which is 9. There we go. A lot of people make that mistake of 3 times 2, but remember 3 to the power of 2 is 3 times 3. So now we're still working inside the parentheses here. Any other exponents, powers, or roots? Nope. So multiplication or division? So 2 times 4 is 8. Okay, so now, yes, we're still inside that parentheses, but it's all addition and subtraction, so it's all on the same level, so we're just going to go left to right. So 12 minus 8 is 4, and 4 plus 9 is 13. So now, excuse me, now that the parentheses is reduced to a single number, what do? We can get rid of the parentheses, and what do we have to remember to put in here? Multiplication, good. So this is 5 plus 3 times 13 plus 3 times 5. So now, again, we go back down through our levels of priority. Are there any enclosing symbols? No. Exponents? No. Multiplication or division? There's 2 of them, isn't there? We're going to go left to right. 3 times 13 is 39. And then we can do the 3 times 5 is 15. And now once again, we're left with only addition and subtraction. In fact, this time it's only addition. So go left to right. 5 plus 39 is 44, plus 15 is 59. We can run into problems like this one. So looking at this one, there are several enclosing symbols. The first enclosing symbol that we see is the fraction bar. That's telling us we have to do everything on top first. So let's go ahead and do that. So we've got the 5 plus 7 times 3. We have parentheses there. Are those parentheses even needed? No, we would have done the 7 times 3 first anyway, wouldn't we? So 7 times 3 is 21. And then we can just do the 5 plus 21 is 26. Good. So the top of this is 26. On bottom, what do we have to do first? We have the parentheses. 8 plus 9 is 17. Now we can remove the parentheses. Do we have to put multiplication in? No, because there's already subtraction there. There's already an operation there. Good. What's next? 3 times 8 is 24. Minus 17 is 7. So the bottom is 7. So our final result here is 26 divided by 7, otherwise known as 3.71428574143 approximately, or 3 5/7. All look familiar? Okay, so now our next step is to go back to the algebra and put in symbols. So I'm going to give you one in numbers, and then I'm going to give you one in symbols. This one's a relatively simple one. 5 plus 7 minus 8, or 5 plus 7 times 12 minus 8. So what we would do first here, of course, is the parentheses. The 12 minus 8 is 4. Then what would we do? Get rid of the parentheses and then multiply. Good. 7 times 4 is 28. And finally add the 5. So 5 plus 28 is 33. But this could be expressed like this. A plus B times C minus D for A equals 5, B equals 7, C equals 12, and D equals 8. What this is saying is, in this formula, we will replace A with the number 5. We will replace B with the number 7. We'll replace C with the number 12. And D with the number 8. So the question comes up, why would we want to do this? It seems a lot more complicated to write it out with variables and then have to put the numbers in than it would be just to start like this. Well, because there are a lot of cases where we're going to run into these expressions and have to put numbers into the formulas and those numbers change depending on the situation. For example, let's say you're doing a coffee table with round legs. I didn't draw that real well. Let me try that again. There we go. These are, sometimes they're called semi-conical legs because they're like a cone with the tip chopped off. You don't need this to know this term, but the technical mathematical term is a frustum of a cone because it's a cone with the tip. It's actually an upside down cone with the tip cut off. But a beveled circular leg or a beveled round leg. The technical term for it is a taper. And if you get into CNC, a lot of your CNC machines, you can actually program the taper. The taper goes off of the big diameter, the little diameter, and the length. So the taper is defined to be the big diameter minus the little diameter over the length divided by 12. The length is divided by 12. All these dimensions are in inches. The length is divided by 12 because tapers are given in inches of diameter per foot of length. So let's say that for this coffee table, we have 16-inch legs. The top of the leg is 2.5 inches, and the bottom of the leg is 3/4 of an inch. So our taper per foot is going to be found by doing 2.5 minus 3/4 on top over 16 divided by 12. So now this is an order of operations problem. What do we have to do first here? The fraction bar tells us we have to do everything on top first. What's 2.5 minus 3/4? Two and a half minus 3/4 is 1 3/4. Then we have to do everything on bottom. 16 divided by 12 is 1.333 or 1 1/3. And now the fraction bar tells us since we got the top to a single number and the bottom to a single number, we can divide. 1 3/4 divided by 1 1/3. So 7/4 divided by 4/3, or 7/4 times 3/4, which is 21/16, or 1 5/16. So the taper per foot for this leg is 1 5/16 inches per foot. So if you're running this on a CNC machine, all you'd have to do is enter that taper, and the machine, well, you'd have to also enter the beginning diameter, the large diameter. The machine would automatically construct that taper. So let's say we have a larger table. So we're going from a 4-inch large diameter at the top to a 1.5-inch small diameter at the bottom over a leg that is 30 inches long. Remember, taper is big diameter minus little diameter over length divided by 12. Take a minute or two and see if you guys can calculate the taper of that leg. Okay, so plugging numbers into our formula, what goes in for big D? What's the large diameter here? 4, good. What goes in for little d, the small diameter? 1.5. Good. What goes in for L?
30.
30. And of course, the 12 is still a 12, so divided by 12. So then our first step is to do what?
4 minus 1.5.
4 minus 1.5, which is?
2.5.
2.5. Good. Then what?
30 divided by 12, which is 2.5.
30 divided by 12 is 2.5 or 2.5. So 2.5 divided by 2.5 is?
1.
1. So the taper on this is 1 inch per foot. What that is saying is for every foot of length, the diameter decreases by 1 inch. So minus 1 inch. Any questions? Now there are all sorts of other formulas that we're going to see. One of them I kind of hinted at a little bit before is going to be the number of, well, let's do number of joists. The number of joists required to cover a certain piece of floor is equal to the length or the run multiplied by, so 12 over the on-center spacing. OC stands for on-center. I know you guys did the little shack for homecoming and stuff, so you guys have done stud walls. And then plus 1 if we're assuming that there's a joist at the end on both ends. So let's say that we have a basement that is 28 feet by 40 feet. And the joists are going to be spaced 16 inches apart. So the first question here is, what does OC stand for? What number goes in for OC? OC is the on-center, which means it's going to be the 16. Now the on-center is in inches. The run will be in feet. Now we only have two options to choose from here. Will it be 28 or 40? Well, the length of a joist is going to go this way. That length is going to be the 28 feet. The run of the joist is how far they have to cover. Not their span, but the run. That goes this direction. That's going to be the 40. So now we'll have 12 over 16 times 40, which is 30, plus 1 is 31 joists. Now, in construction, we often run into examples that are more complicated. Like this plus 1 may have conditions. It might be the number of joists equals 12 over the on-center times the run plus A, where A equals 1 if there's a joist on both ends. A equals a negative 1 if no end joists. And A equals 0 if only one end. So now this formula becomes more complicated. A is going to be changed depending on the conditions that we're dealing with. We'll look at that formula in a lot more detail coming up probably next week. Maybe Friday if we get to it. Let's look at another example, a little simpler, more common example, and that is temperature. We've done measurement conversions. Temperature conversions, because they don't have a common 0 point between the scales, require a formula. Your Celsius temperature is found by taking the Fahrenheit temperature minus 32 and then multiplying by 5/9. So if the temperature is, let's just do 98.6 degrees Fahrenheit, human body temperature. What's that going to be in Celsius degrees? Well, we replace F with 98.6. And we're going to do our order of operations to evaluate that expression. So what is 98.6 minus 32? 66.6. Now we can get rid of the parentheses. So this is 5/9 times 66.6. Now if you're struggling to do this on your calculator, all you have to do is 5 divided by 9 times 66.6. And it pops up 37. So the Celsius temperature would be 37. If we know the Celsius temperature and I want to find the Fahrenheit temperature, it is 9/5 times the Celsius temperature and then add 32. So in your notes quick, I want you to find the Fahrenheit temperature. If the weatherman tells you it is going to be 20 degrees Celsius out today, is that going to be a warm day or a cold day? What temperature is that in degrees Fahrenheit? So take a minute in your notes and plug that in and come up with the degrees.
They give Celsius in Canada, correct?
Yes, they do. The United States is about the only country that uses the Fahrenheit scale anymore.
I think they used to double it and add 30, I think they're all using a rough estimate to tell if it's going to be a nice day or not.
That
was double and add 30.
That's about right. Yes, that should come out really close. So what'd you guys come up with?
68.
68? Okay, good. 9/5 times 20 does come out to be 36. Plus 32 is 68. So if you double it and add 30, that'd be 70. That's really close. Okay, my voice is stretched about as far as I can go for the day. We only have about 16 or 17 minutes left anyway. So I'll give you the second half of your assignment. This is still in the big book. Page 325 through 328. Exercise 12-3. It's evaluating these expressions, putting those values in and solving to figure out what it equals. Again, just do the odds. Hopefully by Friday I'll have a little bit more of a voice.